So in task 1, we explore how the MAT097 model can be used to estimate the human population growth in Mexico between the years of 2002 to 2022. This model is based on a first-order differential equation which is expressed as dp over dt equals to kp. This equation states that the rate of change in population P with respect to time T is proportional to the current population. K is the proportionality constant. To solve this differential equation, we are using the method of separable variables by separating the variable P and T, and then we will be rearranging the terms and integrate both sides until we arrive at the general solution. Then the general solution can be simplified into P equals to AE KT, where A equals to EC, where A is a constant determined using the initial conditions. For our case, we used the population in the year of 2002, which was 519,75645. So when T equals to 0, P will be 519,75645, and we found that A equals to 519,75645. By substituting the value of A into the general solution, we obtain that PT equals to 519,75645 EKT. From this equation, we can also find the value of K. So using this model, we calculated the estimated population for each year from 2002 to 2022. So here is a table comparing the actual population with the values from our particular solution. These figures will allow us to analyze the model's accuracy, which we'll explore further in the data analysis and discussion sections.
Generated three graphs for this task. The first one is a graph of the actual population values from our dataset. The second one is a graph of the particular solution we calculated using the MAT097 model, and the last one is a combined graph that shows both actual data and the model prediction on the same axis. This graph was created by using Desmos. As shown, the model closely follows the trend in the actual population.
Discussion. To predict the population in the future, we need to find the value K first. We use our model P equal to 519,75645 as exponent of KT. By substituting the value of T equal to 1, we could obtain that K is approximately equal to 0.0136. The final particular solution then becomes PT equal to 519,75645 exponent power of 0.0136 times T. To find the population in the year 2033, we substituted T equal to 21, which then we will obtain the value 691,56720. To find the percentage error, we need to subtract the actual value minus the estimated population over the actual value times 100%, which then we will obtain the percentage error of 3.5%. For the past value, we need to use T equal to -1. We calculated that the estimated population is 512,73561. When compared with the actual value, we obtain a percentage error of 0.076%. Therefore, what is the difference? The MAT097 model was applied to estimate population growth. A percentage error is observed when comparing the model result to the actual population value. Although Mexico's population increased over time, but it does not exactly comply with the MAT097 model. This leads to a deviation in data when comparing. The inaccuracy can be explained by the following factors.
The MAT097 model assumes continuous exponential growth, which may not be true in real life. This inaccuracy can be explained by several factors. The first one is economic development. For example, more women tend to join the workforce due to economic growth. The second factor is education. Education enrollment among women in Mexico is increasing. As a result, it delays childbirth and also reduces family size. Lastly, the third factor is migration. Many women migrate for family or work opportunities. Migration can support education through remittances, but it may also disrupt the family structures.
Moving on to our task 2, we were required to find the integral for the equation 3 power of x minus 2 power of x over x plus 2 from -3/4 to 15/4. We are required to find the 8 and 10 subintervals and to find our final answers in 7 significant figures. Let's start off with our 8 intervals. We use Excel to find our final answers. So for A is -0.75, B is 3.75, and C is 8 for the 8 intervals. And the width we obtain 0.5625 from the equation on the top. For X column, we use from the -0.75 until 3.75. And for the fx, we use the equation for our questions and obtain it using the respective row. For the coefficient, we use 1, 4, 2, 4, 2, 4, 2, 4, 2, and 1. For the coefficient, multiply fx, we just multiply both fx and the coefficient column. We obtain the final is 58.2839274. For the integral, we use the equation on the top and obtain the final answer 10.92824. We use the same method for the 10 subintervals. So from A, which is -0.75, to B, which is 3.75, and for the C is 10, which is for the 10 subintervals. We obtain the width is 0.45. For the X column, we use from -0.75 to 3.75, and we obtain the in-between numbers using the equation at the top. For the fx column, we obtain the answer by typing in the equation from our question. For the coefficient, we type in from 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, and 1. For the coefficient multiplied fx column, we just multiply for both the fx and coefficient column. We obtain the sum is 70.85567,101. The integral we obtain is 10.92835.
Simpson's rule is used to estimate area under a graph where you fitting a parabola through small intervals of the curve. So x is the independent variable where it represents the values of the x-axis where you are evaluating the function, and then for the fx is the function you are integrating. It gives you the height of the curve at each x value. Alright, so here is the graph of function being approximated using Simpson's rule. In the first graph, we divided the intervals into 8 subintervals. Each vertical line represents a point where we evaluate the function, and the shaded area represents the approximate area under the curve. So for the first graph, you can see that while the curve is followed fairly well, there's still some gap between the actual curve and the estimate segment. So there's still some error present. And now we move to the next graph with n equal to 10. We are using more sub-intervals. That means that the parabola fit the curve more closely. You notice that the shaded region follow the curve more accurately compared to when n equal to 8. This is because smaller sub-interval give us more points to work with and therefore a better approximation. Alright, now so we are at the last slide where the conclusion is we achieved the objective as we understood how first order differential equation were applied. In task 1, we calculated the population of females in Mexico from 2002 to 2022. We calculated the percentage error between the estimate and also the actual value, and we also determined factors that influence the growth population of women in Mexico. And for the task 2, we're using Simpson rule formula, and with a few steps, we found the integral using fixed sub-interval of n equal to 8 and also n equal to 10. We noticed that increasing the number of sub-intervals in Simpson's rule improved the accuracy of the integral approximation. We also noticed that the curve is smoother and fits better, and giving us a result that is closer to the true area under the function. I think that's all from us. Thank you for listening.